Hi everyone, my name is DiFrancesco and I'm a PhD student at Queen's University under the supervision of Dr. Gene Hutchinson and Rob Harrop. Today I'll be talking about observing 7 years of rockfall activity at the White Canyon using LiDAR monitoring. So here's a quick overview of my presentation. First we'll talk about the motivation and the scope. Then we'll look at the methodology of how we extract rockfall information from LiDAR. Then we'll look at observing 7 years of data at the White Canyon, and we'll discuss afterwards what's next, some applications and future work. And here's a little preview of some of the data from our 7 years of monitoring at the White Canyon and some of the results that we'll look at later on in the presentation. So the motivation of this work is that mountainous terrain presents rock slope and stability hazards, and the smallest of which are typically rockfall. And these can be distributed spatially as well as temporally with regards to a magnitude frequency distribution. And geohazard management often relies on people in the field and in the office working together to coordinate operations. And this can involve the sharing of and communication of spatial information in various different formats, including mileages, reports, GIS. And some examples of this would be this 2,600 cubic meter event which occurred in 2013 at the White Canyon, which might have some reports associated with it, some spatial information, which is kept in a database for future reference with regards to the operation of and maintenance of infrastructure along the White Canyon. And so rockfall databases, they allow us to analyze spatial temporal distributions to learn where and when rockfall occurred. And maybe we can identify some hotspots and areas which we might want to prioritize. We can look at quantifying rockfall hazard with a magnitude frequency distribution, which helps us understand how frequently events of certain magnitudes will occur in the future. As well, we can learn why rockfall events occur. So looking at the susceptibility factors as well as the triggering factors to further understand the rockfall process, which might help us prioritize and prevent some consequences of rockfall. So the motivation of this work as well is across large scale and complex environments, compiling rockfall occurrence is a challenge. There's a visibility limitation from a trackside vantage, as well newly accumulated rock fragments can be indiscernible from older ones. So here we're seeing an example of some photographs along the White Canyon. We can see that along the ditches here, it might be a little difficult for us to notice new fragments that have sort of accumulated here and to document some of the rockfalls that have occurred. Fragments can also propagate beyond our vantage. So there could be some rockfalls that occurred that propagated beyond the track and go unnoticed by our databases. As well, some environments might lack some color contrast that often allows us to notice sourcing areas of rockfall. And lastly, documenting the spatial location of rockfall occurrence might require additional reporting in addition to mileages such as photographs, some key features that help us sort of pick out the sourcing area of rockfall. And so all these additional things in our reports might make it a little more challenging to pass on this information and to make this information a little more digestible. And so here's an example of some of the different vantages that we get from across the Thompson River at the White Canyon and along the trackside. So here we can see this spire feature that's been outlined in red here. And beyond that, from the trackside vantage, we can't really see much beyond. Whereas across the river, we can get a lot bigger picture from behind that feature. And our view is a lot less limited. As well, here's another example on the left-hand side. So data formats and storage are also a concern. So how are we going to share our reports and findings? How are individuals or teams going to be interacting with the data? How do we preserve this information for when experts retire and new members join our team? What I'm getting at here is that these considerations can be addressed by digitizing geohazards and having some accessible storage within databases so that this information is a little more easy to use and can be used throughout our teams and by new members and older members of our teams. LiDAR provides us the ability to digitize geohazards. We're able to digitize terrain at a particular instance in time using LiDAR, And then using some 3D algorithms, we can observe rockfall occurrences or document some geohazards and then digitize them into a geospatial database where we can store them forever and use them as we proceed to monitor. So here we're seeing an example of a LiDAR data set in the form of a point cloud. So what it captures is a series of XYZ points in space. And here we're seeing a particular data set at the White Canyon. You can see some areas where we don't have vantage from the scanner, which are shown as a blue background here, and these are occlusions in our models. So the study site for my work here is at the White Canyon. It's located in interior British Columbia, Canada, and there's an eastern portion and a western portion of the canyon which are connected by a tunnel. And in the western portion we have a 6-scan survey setup, and in the eastern portion we have a 5-scan survey setup. And on the bottom here we can see the timeline in which some of the data we've collected, which has been used in this particular study. And we've collected these data sets using 2 different LiDAR systems, the Optec Iris 3D and the Regal VZ400i. And this is an example of the Regal setup at the western portion of the White Canyon. So going into the methodology, how do we extract rockfall from time sequential LiDAR acquisitions? And here is just a kind of more graphical point of view showing us some data and how we go from some data sets to an individual rockfall events, which are stored as point clouds. And so first we calculate change detection between 2 successive scans, and these allow us to extract the backs of rockfalls and the fronts of rockfalls. So the backs here are shown in blue, and the fronts are shown in red here. And we merge these 2 clouds into an unorganized point cloud, which we then cluster using a spatial clustering algorithm. And now we have individual point clouds which are considered to be a discrete rockfall event, and we can then take these point clouds and calculate some metrics on them. And I'll show you more of that on the next slide. This is a little more complex view of what this workflow might look like. So we have a series of TLS scans. We register them into a common coordinate system, and this often involves us removing vegetation and calculating some alignment matrices in order to get them in the same coordinate system. We then calculate the changing features with using change detection, and we threshold them with a limit of detection. And then we need to classify the changes by using either a classified bedrock model or manually classifying them. And then once we classify them, we can cluster them into individual rockfall events and calculate their metrics. So some of their metrics might be calculating lithology using a surface lithology model, classifying the 3D shape, calculating volume, as well as we have the spatial location of the rockfalls as well as the time interval of their occurrence. And so all these properties of each rockfall event can go into our database. And what you're seeing highlighted in red, in bold red, is some of the things that I've worked on in the past few years, which I'll show you in the next few slides, as well as some other things that David and I have worked on in addition to these other things. But I'll give an example of how these 2 factors within the sort of rockfall extraction pipeline can really change our results. And so we've looked at improving parameters for change detection by using the query size of our change detection algorithm. So here you're seeing rockfalls at a particular point site at mile 109. And we're seeing rockfalls colorized with colder colors being smaller volumes and warmer colors being larger volumes. What we're seeing is when we increase the size of this spatial kind of query parameter, we start to lose some of the smaller rockfalls which are captured with our pipeline. And we're seeing that on the right-hand side where we have this histogram of our rockfall inventories at the mile 109 site. And as we increase this parameter, we start to lose some of the smaller rockfalls. And because rockfalls have a magnitude frequency distribution, once we start losing some of the detailed smaller rockfall events, those make up the majority of our database because smaller rockfall events occur much more frequently than larger rockfall events. And this can be really important because understanding some of or capturing some of the small rockfall events that occur could help us kind of understand the progressive failure of rock masses, and maybe we can learn to predict or forecast some areas which are at a higher threat based on some of the rockfall occurrences which have preceded that time. We've also made improvements to the 3D volume computation. So here we're seeing this point cloud, which is rotating with the front being a warmer color and the back being a colder color again. And we've looked at using algorithms to create a watertight mesh, which we can calculate the volume from in 3D. And on the right-hand side here, we're seeing this magnitude frequency distribution for each different algorithm that we tested. And we can see that the 3D algorithms that we use can have a drastic impact on the magnitude frequency relation that we determine, as well as the hazard that we quantify from it. And so we've come up with a robust method of using this power crust algorithm, which is able to reconstruct very detailed meshes from point clouds for larger objects, while we use this other algorithm for smaller objects where there isn't as much opportunity for geometrical complexity. So now let's look at some of the results of the White Canyon, and this is from 7 years of monitoring. We do have more data that we're working to add to this database. So this particular data set we're seeing is from April 15th of 2013 to March 2nd of 2020, and there's been 52 change detection intervals. We observed over 22,000 rockfall events, and for a total volume of 5,521 cubic meters, from a volume range of 0.001 to 2,657 cubic meters. And again, we see we're using colder colors to visualize small volumes and warmer colors to visualize larger volumes. And a cluster of these kind of colder regions are showing you one rockfall event that occurred that has been that size. So I'll show you in the next slide where we have these subsections that have been outlined here. And individual little clusters of blue here are corresponding to some smaller rockfalls, whereas the larger clusters of warm colors are showing you larger rockfall events. And here we're seeing that 2,600 cubic meter event that occurred in the canyon in 2013, kind of in red or orange here. And we've superimposed events that have occurred after that event on top of the data. So that's why you're seeing some other data on top of that event. And you can see some areas in the White Canyon West. We've seen almost a complete resurfacing here just in only 7 years of our monitoring. And also we can see some examples where in the subsection D here, we're able to observe rockfalls almost 500 meters up at the very top of the slope using LiDAR. Here again is showing this reconstruction of the 2,600 cubic meter event. And this algorithm is very powerful and allows us to calculate much more accurate volume using 3D reconstruction. So on the left-hand side, we see this point cloud, and we need to convert it to a watertight mesh in order to compute its volume. So that's what you're seeing on the right-hand side. For the results for White Canyon East, we monitored from May 26, 2013 to March 2nd of 2020 for 49 change detection intervals. We observed over 27,000 rockfall events for a total volume of almost 2,000 cubic meters, ranging from 0.001 to 47 cubic meters. And again, we do the same thing with the way we colorize our data, and we have 4 subsections again, which we'll look at in the next slide, where you can just see all the detail that we're able to observe using LiDAR monitoring. From the very tops of the slopes to at the trackside, we're able to document individual rockfalls that are at such a small scale and at large scales as well. And we can populate these into a geospatial database. So I want you guys to think back on some of the challenges that I outlined at the beginning of this presentation, and we can really see that when we're looking at this data at a 3D fly-through that we really remove this limitation of visibility of rockfall occurrence using remote sensing using LiDAR. As well as 3D data offers an enhanced visualization and user interaction with the data. So we're able to look at this data in 3D, move it around. It's not really as stagnant on a 2D map as it is when we're in 3D, and we can turn on and off different time steps of change detection, and we can zoom around our site and we can look around. It's very powerful. As well as the long-term storage of data in a standardized format preserves its usage across generations. And that's a really important thing for this LiDAR monitoring, is that this data will never be lost. It will always be there, and it could be really useful in the future as we continue to monitor. And so here's a fly-through. This is of the White Canyon with the 7 years of monitoring information superimposed onto a photogrammetry model. And I'll play this fly-through again at the end of this presentation if there's time for questions. So an application example of this is for the magnitude-frequency relation, and we can quantify a risk based on a frequency of occurrence times multiplied by the different probabilities involved in a particular risk scenario. And one of the most important parameters in this is this probability that a rockfall occurs, and that can be quantified based on a magnitude-frequency relation. So these databases can be very useful for quantitative risk analyses. Now getting into the future work, some of the future work for digital rockfall databases involves the further automation of classification. And so for the White Canyon, since it's so big, we've used a bedrock model in order to help us classify between talus and rockfall occurrences, because we don't want to include talus movements in our rockfall database, as that would skew our results and would really change what our perception is of rockfall activity, its occurrence, and as well as its hazard. And so that process occurs here in mimesis along this kind of rockfall extraction portion of the pipeline. And we need to classify the change between different geomorphic processes in order to get a database of a certain classification of geomorphic processes, which for us in this instance is rockfall. And so we're looking at using some more robust classification, automated classification models in order to better classify between talus and rockfall. And for this White Canyon site, it's particularly challenging. And this mask that you're seeing here was done by manually mapping a photogrammetry model. But by doing it in an automated fashion, shown by Yanni Farmakis, we can really help to remove some of these biases that we have and some limitations that we have by classifying in a 3D program. Some challenges to classification have been shown this summer with those devastating fires that occurred in Lytton and along the canyon, where we have seen the loss of vegetation on the slope. And on this next slide here in this video, we can see that during that time we saw this crazy change detection signature where we're detecting all of this change, which has just been the loss of vegetation. So we also need to think about these things and how if we're unable to classify between the loss of vegetation and rockfall, it's also going to really impact our results. If a bush burning it gets recorded as a rockfall in our database, we don't want that. Some more future work is advancing the application of 3D digital rockfall databases, especially for 3D models. So here you're seeing this model of a fragmental rockfall. And so we can measure this frequency portion of the risk equation, but using rockfall models, we can kind of get the spatial part of the equation. So figuring out whether a rockfall is going to reach the track or not. So understanding the factors influencing the progressive failure of the rock mass is one thing we're going to work on. We're going to work on considering the spatial temporal distribution for 3D probabilistic rockfall simulation, working more on the portability and distribution of data, as well as the visualization and interaction with our data. And I'd just like to acknowledge everybody involved with the project. The Railway Grad has a research program. And here are some references for this work in this presentation. And I'll leave on this fly-through if we have time during questions, and we can look at this fly-through again. Thank you very much.